Thank you. So unique belief propagation fixed point. So first of all, what is belief propagation? So belief propagation is an algorithm that's used to study the behavior of many graphical models. It is independently discovered in several different fields. So it has some other names such as Bayes pairs approximation or the sum product algorithm. It can be applied to many different kinds of models, such as Markov random fields, spin systems in statistical physics, constraint satisfaction problems in theoretical computer science, LDPC and LDGM codes in coding theory, and stochastic block model in network science and community detection. And the belief propagation algorithm can compute anything you want to know about these graphical models, including marginals, correlations, partition functions, etc. It works very effectively in practice, but the theoretical understanding of it is limited. And at least we know that it has very good guarantees on trees. So let me introduce through a tree model called broadcasting on trees. There are several equivalent ways to define this model, but let's take a broadcasting perspective. This model has several parameters. It has a finite set x as an alphabet and a non-negative integer d, which is the offspring number, that is the number of children of every node, and has a broadcasting channel b from the alphabet to itself, and also the invariant distribution of this broadcasting channel. Let us consider an infinite rooted tree T, where every node has d children. And we generate a labeling that is a label for every vertex of the tree through the following process. We first generate a root label from the invariant distribution mu. Then, conditioned on every the label of a node being generated, we generate its children independently according to this broadcasting channel. On the right shows the process of generating labeling of this on this tree. And it can be considered as you have some signal on the root and it propagates down the tree through these edges. And when it goes through each edge, some noise is applied to it. So the belief of propagation comes in when we want to do inference on this model. Suppose we have some observations on the leaf nodes and would like to infer the root label. And you may recall this is an infinite tree, but we can consider like deeper and deeper levels of this tree. And we can use the belief propagation algorithm to aggregate this information upwards. It is exact and optimal on this tree. In belief propagation, every vertex sends a message to its parent, and this message is a distribution on the alphabet. For example, for the tree on the right, we may have an inference process as this, and in the end, you can exactly compute the posterior distribution of the root label. And let us take one more step and consider. So if we fix the label of the node, then the message from this node to its parent actually is a random variable. It's so it follows from some distribution on the space of distributions of the alphabet. That is, it's a distribution on the probability simplex. And the belief propagation operator we consider is describe this evolution of this distribution. In other words, the BP operator is defined as follows. Suppose we start from some leaf observation through some channel P. Then after one step, the observation will be some BP of P, where BP is the operator concisely defined using this formula. And this formula means starting from this channel P, you pre-compose with the broadcasting channel B, and then you take the star power of it D times, and where star power means the independent observation through this channel D times. And by iterating this process, we can get the BP square of P and BP cube of P. So we have this BP operator that is defined on the space of channels to itself, or equivalently the space of distributions on the probability simplex to itself. And so the BP fixed point is just a fixed point of BP. And on a side note, this BP operator also arises from the statistical physics method called the one replica symmetry breaking cavity method, where the fixed point equation is called the one RSB cavity equation. So studying this BP fixed points is helpful for understanding models on trees and locally tree-like graphs. So we have defined BP fixed points. So are there any examples? There is one very easy example that is a trivial fixed point. If you observe nothing of the leaves, then you cannot do any cannot learn any information about the root. From a distribution point of view, the trivial channel is the point distribution at the center of this probability simplex. So the question is, are there any non-trivial fixed points? Before answering this question, let us introduce another fixed point, which is maybe less obvious than the trivial fixed point, but is also very intuitive. It is defined as the limit of the BP, the case power of the identity channel. The existence of limit is not automatic, but it's not difficult to prove. From the distribution point of view, the identity channel is the uniform distribution on the set of vertices of the probability simplex. And this fixed point is called maximum because it is the maximum one in degradation preorder among all BP fixed points. That is, if there is any non-trivial BP fixed point, then the maximum fixed point is non-trivial. Therefore, the question becomes, is the maximum fixed point non-trivial? This is a question that has been studied in probability and statistical physics. It's also known as the reconstruction problem on trees, or extremality or purity of the Gibbs measure with free boundary conditions. And the threshold is called the reconstruction threshold. This problem has been studied in a lot of works. So Keston-Stigam in '66 proved that when d lambda square is larger than 1, then a reconstruction is possible. That is, the maximum fixed point is non-trivial. Here, lambda is the second largest eigenvalue in absolute value of the broadcasting channel B. And this is sometimes tight. For example, Black-Ruiz Zagreb-Bonov.
D is the degree of the.
Yes, D is the number of children of every node. Yeah. Black et al. And Evans, Kayan, Paris, Schulman prove that for the easy model, if d times lambda square is at most 1, then reconstruction is not possible. That is, the maximum fixed point is trivial. And a lot of work studies this reconstruction problems for other models, such as the POTS model, the asymmetric easy model, or broadcasting on hypertree models. Despite all this progress, exact reconstruction threshold is known in very few examples. And in particular, it is open even for random coloring with 3 colors on a 5 regular tree. That is, every node has 4 children. And furthermore, when the exact reconstruction threshold is known, in all these cases, this threshold is actually matches the other threshold called the Keston-Stigam threshold, which is defined at to be at d lambda square equals 1. So the Keston-Stigam result is basically equivalent saying that the reconstruction threshold is at most the Keston-Stigam threshold. This inequality, sometimes equality holds, but no in general. This Keston-Stigam threshold is conjectural to govern the algorithmic phase transition for the stochastic Bohr model. And in comparison, the reconstruction threshold has some relationship with the statistical phase transition for the stochastic Bohr model, but there's no equivalence in general.
So what are you saying, stochastic what model?
stochastic block model.
Block.
Yeah. Okay. So yeah, another question is uniqueness of BP fixed point. That is, suppose you are above the reconstruction threshold, so you have at least one non-trivial fixed point. Then
sorry, is lambda too easy to compute?
Yes, the broadcasting matrix B is usually explicit, and it can be the eigenvalue can be explicitly computed. The uniqueness problem asks whether the BP operator has more than one non-trivial fixed point. And there are actually two other questions closely related to this one. One is global stability that asks if the non-trivial fixed point is globally stable. That is, if you start from any non-trivial observation channel and you iterate the BP operator in the limit, do you get the maximum BP fixed point? And the other question is called boundary relevance, where you define a modified version of the BP operator, which corresponds to a process called broadcasting with survey. And you want to know whether this modified BP operator has a non-trivial, has a unique fixed point. And these three questions are related, and the method, the proof for one usually gives you the proof for all three. And these uniqueness problems have applications to optimal recovery algorithm for the stochastic block model and also a stochastic block model mutual information. So what do we know about these uniqueness problems? On the positive side, for the Eason model, as a breakthrough result of Yu and Poliansky, all three properties hold. For post models and more general broadcasting on tree models, when the d lambda is large enough, d lambda square is large enough, the maximum fixed point satisfies some local stability. They prove that if you are close enough to the identity, if your initial channel is close enough to the identity, then in the limit it goes to the same limit as the identity.
Okay, all right.
And we've made some improvements for the post model. We prove that all these properties hold in this regime, and in certain for certain parameter regimes, this is asymptotically tight when you compare with the negative results. So on the negative side, Yansan also studied the problem they called robust reconstruction, which essentially is saying that the trivial fixed point is locally stable below the casting threshold. This means that if your initial channel is close enough to trivial, then in the limit, it will go to trivial. Therefore, below the casting threshold, even if your maximum fixed point is non-trivial, it is not globally stable, giving an answer to the second question. And we showed that the boundary relevance does not hold between reconstruction threshold and the casting threshold. And we make some conjectures on the phase transition of these uniqueness problems. Below, there are two important thresholds, reconstruction threshold and the casting threshold. And below the reconstruction threshold, the uniqueness and stability problem does not apply because there is no non-trivial fixed point. But we conjecture that the boundary relevance holds. Between reconstruction and KS, the uniqueness problem, we don't know anything about it. I don't have a good guess, but we know that global stability does not hold and boundary relevance does not hold. And above casting theorem, we conjecture that uniqueness, global stability, and boundary relevance always hold. And it will be interesting to answer any of these questions or get a more understanding of these uniqueness problems. Thank you very much. It's my pleasure.
Are there any questions?
It's something called lossy. Beginning, you said lossy loops, lossy trees. What was that? What did you mean?
I didn't say lossy, but you have said
loopy.
Loopy. Yeah, I just mean any graph that is not a forest that has loops.
Any graph of loops.
Yeah. So in practice, BP is the bifurcation is applied to any graph, but we only know that it is exact for the tree, and we have some and we know some good things about it when the model is mean field, that is a complete graph. But for general graphs, people just use it without thinking much about it.
So I didn't quite understand exactly how the easing model enters here. So like, I guess you would like start with a vertex you condition on, and then like sample from the easing model, and then what's the reconstruction problem? Like related to this?
So I define this Cartesian tree problem, and for the easing model, it will be the state space will be the plus minus, and the broadcasting matrix will be what's called the binary symmetric channel. That is, you flip the input with some probability, and you keep it otherwise, and it gives you the same distribution as the free boundary easing model.
Okay, so I start at the vertex and then I go to the neighboring network and I flip depending on what my vertex is.
You flip by throwing a coin.
Okay. And I'm trying to align with the one that I started on, I guess.
You're not trying to.
I started fair coin, right? So I'm preferring this.
Sure. Okay, yeah, but you can also consider anti-fermenting models.
Does your non-trivial point related to phase transition? I think no or not.
So so the relationship is best understood in the stochastic block models, and okay. So I think the relationship between the random graph models and the Cartesian tree models is in the stochastic block model, if you have no reconstruction for the corresponding Cartesian trees, then it is impossible to recover. But for other models, sometimes the threshold coincide. For example, for many easing models, the phase transition threshold for the easing model on random graphs, they coincide with the reconstruction threshold. But I think they're proving a case by case.
I go back to my first question. You take an arbitrary graph, what's the layers, what's the leaves?
So if you consider a locally tree-like graph, then the
locally tree-like.
Yeah.
Yeah.
Any other questions? Let's thank the speaker again.